So to start us off, I wanted to just kind of preview our workshop agenda today, because we're going to talk first about these different components that have been developed by the different partners that we have in iFishIENCi. And if I can just get this on here. Yeah. We're going to go through the presentations from our different partners and the different components. And I also want to preview that we have a half hour of discussion and dialogue, because this is the chance for the viewers online and the visitors here in the room to give us feedback on the development. We want to talk about the market pull of this technology of iBOSS, the techno push, additional components that people maybe have ideas of, and the regulatory, the governance aspects. What are we missing here? Also bringing some of the policy roundtable discussion into this specific technology. So without further ado, I'd like to introduce Frank again, Frank Legal for EGM, who's going to talk a little bit about iBOSS.
Good. Thank you, Dorothy. So me again for the ones who were there already this morning. So as Dorothy explained, we will go a bit more in detail into the iBOSS, and what we'll do this afternoon is taking the context of RAS system. So I will start with the two slides kindly provided by Thomas from Acrobiotech on the requirements or the needs to move from traditional RAS system to smart RAS. If we look at RAS systems, we have a number of challenges. First is the high pollution risk, which are associated with RAS system, in particular everything related to mass mortality that you encounter into such circulating systems. The high investment cost, it's a costly system that you have to go through. There are other competitive approaches to RAS systems. So if you want to develop, to deploy the RAS systems, then you have to maintain competitive on financial aspect as well. And we need to move that competitive advantage, and also looking at the sustainability advantage that RAS provide to the market. And if you want to do that, then you need another being able to exploit it. You have to better understand your system to fine-tune, to optimize the system, and then improve your design so you can replicate it quite easily. So this is what has pushed IBT to develop in the context of iFishIENCi the smart RAS approach, where if we start from the bottom, we do measurements, traditional measurements on water quality. And we are looking at traditional one, dissolved oxygen, but there are some other parameters that came during the project to increase the coverage of water quality parameters that we are measuring. What is the feed usage? How much feed is being distributed, and which feed at which point in time in the day? What is the observed fish growth of the fishes? And also, because it's linked, what is the overall energy consumption of the system? Using all these measurements, then we can control a number of aspects of the RAS. Obviously, all the water flow, intake of water, all parameters, temperature, dissolved oxygen, and so on. But also we can optimize the disinfection of the system, and as we progress in the project, all feeding aspects that are being improved. Also mechanical filtration, lighting, and the ideas, because if you know energy consumption, if you are looking at energy consumption of a pump, for example, in a filter, then you can anticipate that there are some requirements to go and clean the pump before you actually see it from the RAS system. And at the end, all of this to influence fish biology, behavior, all water quality parameters, the filtration, and at the end also the discharge quantity and quality of what you are discharging. So all this loop is what is the smart RAS. So all along the workshop we will see how with the different inputs from the partners we manage to move from RAS to smart RAS.
Quick reminder on this morning, I will go fast because you heard it this morning already, but we want to deploy the system, and what the approach was not to go for a locking situation with independent solutions, neither to go for an all-in-one package solution, but rather to go through that interoperable solution. So really looking at the different assets brought by the partners in the project and how we could get them to interact from a technical perspective, but also from a business perspective at the end. So not forgetting that, okay, beyond what we do here, it's not only technical, it's at the end business. Reminder, we are based on standards, so we avoid reinventing the wheel, so it can be used by others. These specifications are defined by other consortia, so it's quite wide in the aspect. And because it's easy to understand, we have this central platform where we collect data from different providers. We can use the data on application in dashboard, and we can process, play, let's say, with the data. Now, how it looks like if we go a bit more to the reality. So we have a number of different boxes. There is the middle, what we call the iBOSS data core, which is really the place, let's see the database, okay, where data is coming in and where data has its representation, so it can be used by all other components. If I want to put data there, then I need some connectors. So there we have a number of different connectors in blue here, which are able to adapt, to collect data, input data streams from different sources and transfer it into the same format in the middle, so it can be used by other components. Other components, if we look on the visualization aspect, there are some simple components. So the name here, Grafana, Superset, are in fact open source components, so there are even free components. If you go on the web, you can download, install them on your side, and connect to this kind of platform. So it's really based on this idea of building a complete ecosystem of solutions. So Grafana, which is simple dashboard, and Superset, which is more for business analytics, so where you can visualize the data, but you can play, you can do even some predictions based on the data, so it's really to understand what is your data. We worked a lot also on the models. You will see video analysis, how we do process on the video stream. There is EcoSounder data, FishMet, which is a fish simulator which has been turned into a digital twin, which is being used in the project as well. And at the end, all this is used to calculate the optimum amount of feed. On the spot, on the site, we have what we call the iBOSS edge, because there is always a trade-off. Okay, should I put things in the cloud, transfer all the data, which can be costly? Should I keep the data locally, process it locally? Sometimes we may have some security, privacy aspect as well. Sometimes the farmer says, okay, I don't want the data to go out on my site. Sometimes it says, oh, I don't want to bother about that. Please take care of it. But in any case, so we can have this box, and we have this black box, which is about security, which is quite important. So all transactions are always, people are authenticated, all transactions are encrypted, and so on. So we ensure security everywhere. This is blocks we have here, and in red there, it's interesting because that's third-party cloud. So we can have other partners, and for example, in the project, Biosensor and Doxiguard play these roles of being external companies and interfacing through the same interface with the system. So they were able to push and collect data also with the system. They were contributing in other places, but it was quite interesting to show that we were really able to build that complete loop. So I put some logo here. It's what we do use as standards. Stelio is the data core, and then we have all partners which have been contributing here and there. I don't go into the detail of each block because then it could be a one-week workshop, but that's the overall idea. So now what we will see in the next presentations are through different aspects of different building blocks which have been developed here, so you better understand how we have been able to progress in the project. Thank you.
Thank you, Frank, for that overview.
Hi, I'm going to talk about our model. It's called FishMet, and it's simulation made by a kind of very advanced specialization. We are not probably at this point so advanced, but we can make a simulation of the fish. And our vision is to make a simulation model of the whole fish, including the gastrointestinal system, neurobiology, stress, and everything else. And the starting point is the fishnet model that just represents the fish feeding, appetite, energetics, and growth. Sorry. It differs from the traditional models that are based kind of on a kind of equation. You have an x and y, and you can calculate y based on what the value of x. In our model, the fish has agency. It can make its own decision whether to eat every feed item or pellet or not to eat. And it depends on its appetite. That is, again, a result of multiple feedbacks from the neurobiological systems, stomach fullness, and other factors. And the output is dynamic energy budget, growth, and behavior. The model is based on the knowledge of the fish physiology, and we just try to implement what we know about fish physiology. We follow the famous motto of one American Nobel Prize laureate, that what I don't create, I don't understand. So we try to create a digital fish. In this case, we start with a simple thing. Our vision is to make a kind of model of fish in the context of modern precision fish farming. And the vision in general is to create a digital twin of the whole farm with the fish, decision model, data ingestion, and logistics and everything. So the whole farm can be represented in a digital laboratory. And if you need to do some optimization, or if you need to predict what will change depending on on other changes, then we can model this and get the output and get the result. And then optimize real farm functioning. And this is the starting point. We only make a model of fish, not everything else. This is a simple outline of the model. It starts with feeding, the falling of food pellets into the environment. The fish makes a decision whether to eat or not to eat it, depending on its appetite. If it eats the food item, it goes to the stomach, then to gut. There is a processing in the stomach and gut. Food is absorbed. The energy is getting from the food. It contributes to the energy budget and to growth or activity. And the part of the feed that is not absorbed, then it goes to evacuation. And it creates a kind of loop. And in this case, the digital fish is kind of living in the digital environment. It's like a computer game. It's not like traditional models like a formula. The input is physiological characteristic of the fish, the feed scheduling, and it's all. And output is fish behavior, feed intake, growth, and energetics. The model is implemented in the computer program that has different interfaces, like this show the screenshot of command line interface. They can be scripted, and we can run different scenarios. There's also a graphical interface, because the model is also a research tool, not only this practical application. The input data follow the open standards like JSON and human readable text files. The output, we can output quite a lot of parameters of the fish, like energy budget, body mass, growth, instantaneous growth rate, and so on. And the modeling can be conducted over different time scales, like 1 day or a week or whatever we do. This, of course, the longer simulation runs, the bigger is uncertainty, and the bigger the error. Food intake and stomach content, stomach fullness. The idea of the model is to to make it useful for what-if scenarios, like if a farmer decides to make some kind of change in the food scheduling or so, then he can predict what will be the result, the output of this change. And the value of model is, the start point is to try to explain and account for the real things. Before we can predict something, we need to make sure the model is working. And this is a demonstration of a simulation of 1 week of fish growth based on real data from the fish feeder. And it shows that we have quite good result. The growth is very close to the real growth in the farm. It shows some other, a couple of other screenshots. And the model is integrated with the iBOSS. It's a separate thing, but it's also integrated. It can be integrated with many different systems. We have a dedicated server running the FishMet model that interfaces with the iBOSS, and it can the data can go back to the fish farmer through the iBOSS interface. We have a website with the description of the model because it's transparent. It's not like artificial intelligence models based on huge number of parameters and neural networks. It implements the real fish physiology knowledge. And this is a plot, diagram of interaction with the iBOSS. All the simulations are done by on demand. When we need some simulation data, the simulation parameters are sent from iBOSS to FishMet. Then the software creates all the scenario scripts, run simulations, and we get back the results into the iBOSS. Okay, thank you.
Thank you very much, Sergey. Great to see our digital fish in action, and that the results are promising.
Yes, yes.
Excellent. And now we have our colleague from BioOceanor, Nicolas Prost, who is joining in from France, and we will get him on the screen. So we're just going to make sure that we can hear Nicolas in the room, and to fix that, we'll have you, Christian, from Oxygard, telling us about the Oxygard work in iFishIENCi.
Yes, hello. I'm Christian. I'm coming from Oxygard, and I'm here today to talk a little bit about how we connected the monitoring system, control systems into iBOSS to get water quality measurements up in the cloud. So, for enabling this aquaculture 4.0, the most obvious thing is to have the water quality parameters and measurements up into the cloud. So we developed a data sharing module for our cloud platform called Cobalia, and Cobalia is a farm management system we have that does everything from monitoring, control, and feed management, and stock management, and task management, and stuff like that. And now it also does iBOSS. So we connected it. Yeah. We demonstrated at 2 of the partner sites, one at HCMR in Greece and the other one at AgroBiotech. At HCMR, we deployed a system with 3 DO sensors and temperatures at different depths, and a single pH sensor. Those sensors are connected to a specific system that handles the measurements and the monitoring, and it's sending the data up to our Cobalia. The only thing it really needs is internet connection, and at the site at HCMR they have an internet connection that's shared by the different systems they are running at the sea cages. And from there that goes from Cobalia to iBOSS. A thing that's worth noting is that the data is actually owned by HCMR, and they control what to share and who to share it with. So they just decide to share it with iBOSS, and that's really, so we're sharing all the data from here, but it's up to them. So it goes from the probes here and up to the Pacific, and then to Cobalia, and then further to iBOSS. Yeah? At Aquabiotech, they already have a complete system with lots of Pacific systems. They also have a OxyGuard commander system on top of that handles the control of the feeders, control of the lighting, and a bunch of other stuff. It's all connected in a production network, and that production network does not have access to the internet. And that's a security issue because it's the simplest way and relatively reliable way of keeping people out of the network. But it makes it a little bit difficult for the data to get out. So we discussed it with the IT guys at ABT and decided to make a proxy service for the monitoring PC, because the PC is the only thing that's connected both the production network and the internet. So for the Pacific to actually send the data out, it's sending it through the monitoring PC. It's a little bit, it's the long way around, but it does the job. We ended up monitoring 12 tanks in what they call Base Zero at Aquabiotech. And it's with DO and temperature, and they have a pump sump also, which are measuring pH and redox, and I believe there's also a CO2 sensor there. And we have a new ozone sensor we also tested there. Yeah. They also do manual laboratory tests every day at Aquabiotech on the wastewater, and the data normally goes into Excel sheets or something like that, but we put it into Cubalia as well, so it's just like another probe, and it's also possible to share that data with iBOSS. When it comes to feeding, the site has drum-style like feeders from Avrotech, and they are controlled by an OxyGuard feeder controller. And it's the fish master sets it up to feed a certain amount a day at a certain time periods. And the way the controller works is that the fish master sets it up, and then it just runs by itself. And we ran, I think, 1.5% of the body mass at the trials we did. The idea is that we want the iBOSS to have data from, for example, the FishMed model, or in this case, we actually used the camera for behavioral data to generate a feeding score, which we'll be hearing a little bit about later. And from that feeding score, we could say something about the hunger of the fish and manipulate the feeders in how much it's actually going to feed. So if we were planning on feeding 100 grams and the feeding score was 0.9, we will only feed 90 grams. And at the next interval, we will measure a new feeding score and apply that, and so on and so on. And that's when the feeder is feeding, it registers how much it's actually feeding and sending that back to iBOSS, so iBOSS gets the actual amount of feed it's used. And when we feed the fish, they tend to grow. And so for one of the trials, we also took all the growth data, put into Cubalia, and that's also possible for us to share that with iBOSS, so you could optimize growth models in iBOSS as well. So what we achieved was that we connected our platform to this iBOSS open platform for sharing the data across multiple vendors, platforms, clouds, algorithm, enabling us to use the best algorithm independent of the vendors. So we also added the possibility to take these measurements that's normally done in Excel sheets or Post-it notes or generally offline and put it into to iBOSS and do better predictions and possibly better predictions. We also showed that the iBOSS can actually control the feeding from the behavioral data. However, we ran into a problem with the IT infrastructure, and that's something we see at most RAS facilities, that it's really protective about the production network, which makes great sense, but it makes it very difficult to get out of the system. And that's one of the bigger issues and one of the issues, but it's solvable. That's all for me. Thank you.
Thanks a lot, Christian. Really wonderful to have OxyGuard as a partner in iFishIENCi to work on these technical solutions. And I like it when Christian says it's solvable. We can do that. So now we're going to ask the question, have we solved our listening issue with Nicolas. Nicolas, can you hear me?
Yes, I can hear you. Can you hear me?
So, can you help us answer the question on how you detect if the fish are full?
Yes, I can. Can you confirm me that you can hear me?
Go for it, Nicola. We're all ears.
Okay, great. Thank you. Sorry, I didn't. Okay, so I am responsible for the development of the fish society detection model in the aquaculture demo site. So this is analogous to what HCMR presented this morning in open cages, but here we have the constraints of RAS, and I will explain how we are defining the feeding score that Christian is using to control the automatic feeder. So as to have a better context, here is what the fish look like in the RAS. So on the bottom right, you can see in blue the automatic feeder. And the goal here is to measure the feeding behavior of the fish based only on this video footage, without using any kind of sensor in the cage. And we're trying to optimize the automatic feeding. So right now, in order to feed the fish in the RAS, you have two options. First option is manual feeding. So the advantage is that you can stop the feed in function of the reaction of the fish. You can stop it when the fish are done eating, but this requires the intervention of a qualified human. And you can't really study the behavior of the fish because it's biased by the presence of a human. So the alternative is automatic feeding. So this time you don't need the human, but there's no solution yet to really take into account the behavior of the fish. So you have to predefine it based on just the weight of the fish. So our proposal here is to define an AI-assisted automatic feeding that we use on a once per feeding basis, meaning that during one feeding, we monitor the fish activity. We use it to derive an indicator of the satiety of the fish. And we use this indicator in the next feeding to adapt the feeding schedule. So in order to do that, we had to define indicators to measure the behavior of the fish. And we used for that two mathematical tools, a deep learning model to detect each individual fish on each frame of the video, and another model based on Kalman filters to track those detected fish throughout the video stream. And this enabled us to compute 4 different indicators of the behavior. So the first one is the most obvious, is the speed of the fish. So we're measuring each individual fish, but that's too much information, so we have to aggregate it. And in order to eliminate extreme values and measurement errors, we're only looking at the median and the first quartile and the second quartile of the speed distribution. That gives us an idea of the group speed. This is complemented with 2 other metrics which are designed to identify specific swimming behaviors. The first one is the rotation, meant to detect actually the default swimming behavior of the fish when they are swimming in a circle in the tank against the current. And the other one is a convergence metric meant to identify when the fish are rushing towards the fish. And the last metric is the number of detections, the number of fish detected. So sometimes in very rough conditions where the water is very agitated or the light is bad, we can see fewer fish. So that gives us a quality indication on the other indicators. So I want to show you that these indicators are complementary, and that you have more information than with just the speed on these 2 examples. So here you can see the top curve is the speed, the middle curve is the rotation, the bottom curve is the convergence, and we look at how these 3 indicators change in time before and after a feeding pulse, so when the automatic feeder drops some food. These are actual examples. So on the first example on the left, at first the fish are at rest. They're really swimming very slowly with no rotation pattern. And when the feeding pulse arrives, you can see a convergence peak at the bottom because they're rushing towards the feed. And afterwards, the speed curve, you can see that it increases and it stays high. So after they have rushed towards the food, the feed starts swimming and are very agitated with no specific rotation pattern. On the right example, the fish have eaten already, so they are already swimming quite fast, but in a synchronized manner. So you can see on the rotation curve that there is a steady rotation, and when the feeding pulse arrives, the rotation is interrupted. So in this case, having the rotation and convergence metrics brings a lot more information than the speed, which itself then does not change much at the moment of the feeding. Okay, so this is a lot of information which can be interpreted by a human. We can make scientific analysis on that, and we can really tell what the fish are doing, what are the swimming patterns, and possibly we could improve, because it is based on the technology of individual fish tracking, we could potentially improve it to do individual monitoring and tell which fish are hungrier than others. So we could continue this exploratory and research study. But from an operational perspective, we need something a bit simpler and more efficient, something that would require less computing resource to be able to run in real time on CPU, and we need a synthetic indicator, something that really allows to control the feeder with something that quantifies the notion that the more active the fish are, the hungrier they are. And that's how we're going to define a feeding score with this new operational solution. So for operational purposes, we replaced these individual speed and rotation and convergence metrics with a global metric, which is a proxy of the activity of the fish. And technically speaking, it is based on essentially the difference between two successive frames that we are monitoring throughout the video. So it's really a group metric. We have lost the notion of individuality. And on the right part of your screen, you can see screenshots from the iBOSS platform. On the top, you have the status of the feeder. So each green line is a feeding pulse. So when the feeder drops food, and you can see the fish activity on the bottom during the feeding. So there is an activity peak at each feeding pulse, and then you can see that after the feeding, the fish start being more going back to rest. Okay, so based on this activity measurement, we are going to define the feeding score as basically the average activity during the feeding, and more specifically between the start of the feeding and 15 minutes after the end of the feeding. And we do that to take into account the time it takes for the fish to go back to rest after the end of the feeding. And this is really a single indicator that quantifies the notion that the more active the fish are, the hungrier they are. And we use this to control the automatic feeder with a simple rule. If the feeding score is, for example, 1.4, this means that the fish are 1.4 times as active as normal. So the required action is to give them 1.4 times the normal amount next time. And I will add a technical detail, which is that this feeding score has to be calibrated on design historical data, so that in a normal feeding week, the average feeding score is about 1, because it's not the case by definition with the activity, the way we define the activity metric. Okay, so this time, this activity measurement is done in real time for the whole day. And this means that we could go beyond the measurement of the activity during the feeding. We could actually use the whole day but that will require a lot more work because we need to understand all the dynamics of the fish behavior. So that would be next step. We could also potentially use it in real time to define when to start and when to stop the feeding, and not just the quantity. Okay, just as a finishing note, I think Gianmarco will present the result of the demonstration in the presentation afterwards. But I just wanted to show you an example of a typical day that we monitored during the demonstration. So you can see the activity of the fish. There are 4 feedings. So at first, the lights turn on in the lab around 7 o'clock. So the fish were really still at the beginning, and they start moving. There's the first feeding at 9 a.m. where the feeding score is a bit lower than normal. The fish are not super active. And then the feeding score increases a little bit throughout the day, with the maximum at the 4 p.m. feed. Okay, thank you for your attention. That's all for me.
Super, super interesting. And you previewed a little bit of Gianmarco's demo. And our colleague from Aquabiotech Group in Malta, Gianmarco Cusumano, is going to show us how to go from normal RAS to smart RAS. Take it away.
Thank you. So welcome everyone. Thanks Dorothy for introducing me, and thanks for the iFishIENCi project to support our research. So as Dorothy said, today I'm gonna talk about how to move from RAS to smart RAS, and how to demonstrate the technology, the smart RAS technology that was developed in the iFishIENCi project and experiment performed in Aquabiotech about the use of Atlantic salmon in the smart RAS system. So first of all, I would like to highlight how the aquaculture industry has grown Sorry, there is something. It's going automatic. Sorry. So, how the aquaculture industry has grown constantly in the last decades, evolving from. I don't know what's happening. Sorry. May I? Yeah, but this is going automatically. Let's see now. So, I'm not touching anything.
There you go.
Okay.
It's landed.
Yeah, but I need to go.
Just go back if you need to.
Back. Okay. Let's see now. Okay. So, as I was saying, how the aquaculture industry is evolving from labor intensity production to a more mechanized and standardized production. So, of course, to achieve this one, we need a new intelligent aquaculture model that in the case of iFishIENCi, it was the aquaculture 4.0. Of course, the iFishIENCi project is targeting this one by the improvement of the production system and the monitoring system of the aquaculture production, the optimization of the feed utilization through the smart RAS technology, and the monitoring of the fish throughout the day in a continuous way. So how we did do this one? So first of all, we introduced the biology online steering system of iBOSS that it was previously described by Frank and by the other colleague. We performed at Aquabiotech several fish trials to record data for the development of the technology, and then we analyzed the feeding behavior of the fish, so the behavior that the fish were showing during each feeding event that were used for the technology. Okay, so in one word, this one was the smart RAS technology, and sorry, just a second, and it was a synergistic work between different partners with different background. There was Aquabiotech Group that I'm representing, Biosenor, Oxygard, EGM, and University of Bergen. So, our ABT RAS system was turned into a ABT smart RAS system, and specifically, it's of course located in Malta. It's equipped with 12 tanks of various volume that it can be as, depending the species and the requirement of the trial. The capability of our system range between fish nutrition, so testing of novel protein, additives, pigments, and digestibility, but of course also assessing fish behavior, climate change prediction, stress tolerance, and vaccination. As our system is quite, let's say, the parameter can range widely, so about the salinity, about the temperature, because we can adapt our system to freshwater, seawater species, cold water, and warm water species. Of course, as our system is equipped with UV disinfection, protein skimmer, automatic feeder, and swill separator. What is peculiar of our system is the continuous monitoring system, that is an Oxyguard Pacific unit, that constantly check parameters such as oxygen, temperature, pH, and redox potential. And it is also connected to the iBOSS system. So all the data that are produced in our system are directly pushed into the iBOSS cloud, and they were, of course, processed for the development of the technology of the smart RAS. Each tank is equipped with a camera with which we can monitor our fish. So, as I said on the first slide, there were several trials performed at Aquabiotech to process enough data to develop the technology. This one can be summarized in 3 different phases. Phase 1, where we aimed the real-time detection, tracking, and monitor of the fish, and it was what Nicolas previously described in the presentation. So the development of an algorithm that can evaluate the behavior of the fish during the feeding event. So for this reason, we used 400 salmon at average size of 13 grams, freshwater, kept in freshwater, a duration of 10 weeks, and fed at apparent satiation 4 times a day. Of course, the fish were recorded 15 minutes before and after each feeding event. So our idea was also to let the fish adapt to a low human activity in the system. So we are performing different trials to let the fish adapt to this new condition. During phase 2, the aim were to develop a scoring system that can take the data from the real-time detection and providing us data between a number comprehensive from 0 to 2 and analyzing the feeding behavior of the fish during feeding events. So for this reason, the same fish used during the first experiment we're using during the second one. Of course, they were bigger. The duration of the trial was of 3 weeks, and in this case, because we wanted to stimulate the activity of the fish during the feeding event, we discussed with the partner. At the end, we come up with 3 different feeding ratio of the fish, each one that lasted for a week. So during the first week, fish were fed at 1.5%. During the second week, half of the ratio was delivered to the fish, so they were fed at 0.75, while during the third week, they were fed until up to 3% to achieve satiation. This one was done to stimulate, in the case of the half of the ratio, to maximize the hunger, so to have a scoring number that it was higher and close to 2. While during the third feeding, in our prediction, the scoring system should have been close to 0 at the end of the feeding day. As I said before, the fish were recorded 15 minutes before and after each feeding event. During the last trial, in this case, the technology was already partially developed. So the aim was to compare a feeding based on body weight, some percentage of body weight of the fish, versus a feeding based on the scoring system that we developed during phase 2. And of course, as a complementary data, we analyze also the growth performance of this fish. In this case, we use 2 tanks, same volume, same number of fish, same average weight. In this case, they reached 60 grams in average at the beginning of the trial. The duration was still 3 weeks. And the feeding method, as I said, 1 tank was fed automatically at 1.5% of body weight. The second one was fed still automatically, but based on the scoring system that we developed in the previous phase. fish were still recorded 15 minutes before and after each feeding event. So this one is just to show you how in our facility the technology is installed. So as you can see here, this is a tank with 400 Atlantic salmon, initial average weight of 15 grams, with a camera placed above the tank, so you can see how each single fish can be easily detected. In these other two videos, I wanted to show you what's the difference between an automatic feeding event that happens in a tank with Atlantic salmon. This one instead is a feeding event with hand feeding. So the fish previously as a stock, they were used to receive fish by hand from our operator, while in the second part of the trial, some of the fish they were fed automatically. So as you can see here, when the feed was delivered, some of the fish they show the typical behavior, so they are tricked by the throw of the feed in the tank, so they're coming up to the surface, triggering also the other one to repeat the same behavior. In the case of the automatic feeding, the behavior is a bit, the feeding behavior is a bit delayed. So you will see a bit more of time between the throwing of the feed in the tank and the actual feeding of the fish. Sorry. So, talking about the results. In this graph, I wanted to summarize the result of this trial. Precisely in the first graph, you can see here number ranging from 0 to 72. This one, the actual number of feeding that have been provided during the 3 weeks of trial performed. And as Nicolas said before, the fish were fed 4 times a day, 9, 11:30, at 2, and at 4. The two tanks were fed, as I said before, in 2 different ways. So tank 2 was based on body weight. So as you can see here, there is a steady line. And the amount of feed delivered per day, it was the same, and in this case per feeding, it was the same at each feeding point. Of course, here there is an increase of feed amount based on the growing of the fish, so the fish were actually weighed and the ratio was recalculated. In the case of the smart RAS feeding, as you can see here, the amount of feed per feeding events, it was different, meaning that the hunger show of the fish was different in each feeding event, and the system was automatically adapting based on the behavior showed from the fish. The second graph is showing the same result as the first one, but in the case of the line, they correspond to the daily amount of feed and not the one per single feeding event. So the trend is similar to the first graph. In the third one, I wanted to highlight how tank 1, that it was the one fed by the scoring system, the actual amount of feed that was delivered during the experiment, it was less, or like lower, than tank 2. So the feeding using scoring system shows a more dynamic feeding, which is indicative of a natural variation in hunger. Sorry, it's not moving. Okay, yes. What about the grow performance? As I said before, there were a complementary data of the trial. We didn't have any replication of the tanks, so this data they must be taken as they are, because there was not significant power of the analysis. So as you see here, tank 2, that was the one fed by percentage of body weight, has a higher growth rate, while tank 1, that was the one fed by the scoring system, shows a lower growth, even though they show both a similar trend of growth. In the case of the FCR, see as it is, the technology is not improving the growth of the fish. But as I said before, it was the first experiment, so we want to further develop this technology. So following this graph, the FCRs, it's higher in the tank fed by the scoring system compared to the one fed by percentage of body weight. To conclude, in our case, so in Aquabiotech, what we achieve with this technology first, we have a continuously monitoring of the fish in real time throughout the day. That is really important for us because of the nature of our system. So we can act fast when we when we know that there is a behavior that is not natural, so a natural behavior of the fish. Of course, this one might lead a reduction of costs related to feed use and also human activity during husbandry, because we were trying to adapt our fish to a low human activity in the system, and as a company that has several trials during the year, this might be, of course, a milestone. The optimization of feeding through the reduction of waste, of course. And as I said before, this one was a synergistic work between partners of different backgrounds, like aquaculture, AI, academia, and data science, that usually they work separately, but in this case, it was a collaborative effort among multiple organizations, and we hope that this one might continue in the future. So, feeding based on the activity allows for variability in hunger throughout the day and over a longer period. So we were studying how the fish were adapting to a different type of feeding, and as our colleague Nicholas said before, we saw how the fish are active in a different way throughout the day. During the morning they are less active, and they keep evolving during the day until a peak that is usually in the middle of the day. So what we need still to do? First of all, we show that the results are suitable for a pilot scale system, but in our case we we test the technology only on Atlantic salmon. We would like to test this one in different species, ranging from freshwater to seawater species, cold water, warm water, for example sea bass, sea bream, catfish, tilapia, and so on. And of course, the feeding strategy based on the activity of the fish instead of the percentage of body weight needs to be further developed. We aim to, of course, scaling up to the industrial level. And I would like to thank my company for providing us all the technology needed for this trial, and my colleague Freya for working with me and with the other partner to achieve these results.
Thank you very much, Gianmarco.
You're welcome.
Just stay a second, because there is a question from online audience. Were there any water quality or other physical parameters measured at the same time?
Okay, so in one of the previous presentations, the one from Christian, he said that we perform water quality daily in the system, at least once a day, for parameters like nitrogenous compound, while all the other water quality, temperature, dissolved oxygen, pH, whatever, they are continuously monitoring through the monitoring system, and the data are in real time pushed to the iBOSS system, and in the case of the presentation of Christian, also in Cobalia.
So this is all going on in the background. Excellent, great. Thank you very much, Gianmarco. I'd like to invite Frank from EGM and Boogie, Bjørgafur Halvarsson, also up, because we're going to put this in a little bit of a bigger perspective. We talked about now the iBOSS ecosystem. But we also have a larger ecosystem, both physically and in an industrial way. And from the Seafood Innovation Cluster here in Bergen, you guys have a lot of experience in getting industry to share data and trying to push this idea. That's been part of this AquaCloud project.
That's correct. We've been working on it for almost 8 years now. Firstly with members in the cluster, because that's natural for us to pick from. But now we actually have 11 companies and approximately 50% of the Norwegian biomass calling home. 50%. Mm. So
and the Norwegian biomass is how many tons?
About the swimming biomass, let's say 1.1 million tons, so it's 500,000 tons. Mm. And they are spread, as a biologist, I love the spread in our sort of supplying companies. There's a north-south vector, so you have the climate specters of Norway. But there's also in-fjord exposed areas, which will also give you that temperature or salinity or environmental factors. And everything aggregated, I think we are getting some 50 parameters every morning at 9 o'clock. Mm-hmm. The most important is number of fish in the cage, and this is time-stamped, geo-stamped, and location-stamped, and production area-stamped, so that's the metadata. Mm-hmm. Where, when, what, and why, literally. And on what depth the sensors are reporting from. Mm-hmm. Size, average size, number of fish, mortalities, We are starting to develop reason for mortalities. We call it the CSI project, understanding why the fish died, and because we have used a category called other quite a lot.
And natural mortality is a big issue in Norway.
Yeah, but not only natural mortality, that's other, but viruses, bacteria, parasites,
mortality.
Treatment. So what happened actually to the fish? Because if you haven't measured it, you cannot react to it. I think we can agree on that. And with these companies backing those standards, we're also getting impact from other companies who are not in the aquaculture system, but just see the common sense of working towards this kind of standards.
Yeah.
But we are also pushing for standards where we actually use the same vocabulary. We call things the same name. Sea lice has, when I started mapping the data, sea lice had 6 types of, or 6 nomenclatures. So it was mix of English, Norwegian and Latin in all the permutation you could imagine.
Yeah.
I always say we were just lacking bloody sea lice. That was the only. So by working together with companies for so long time, very important part has been standardization to get the data on equal quality. In general, improving quality, adding sensors and putting them at similar depths, but also developing the governance. What can we do with data? What data can we share openly, completely public? And that's the environmental data. I mean, you can't hide the temperature in the ocean. But when we go down to the deeper, like the mortalities or the biomass of companies, you can absolutely not go public with that, because that would be inside trading, and that would actually put the fish farmers in all kinds of problems. And aquaculture as a project and company as well.
Yeah.
So we took a full year in working out the governance and getting everybody aligned with that, and it's
what data is shareable, what data is not shareable.
Yeah, and what do we do in the next level when somebody has developed a product based on our data?
Yeah.
Where lies the ownership? So that's also a very sensitive area, because somebody's building a product on your data. So where lies the ownership there within?
So what is AquaCloud? What's the ambition there for AquaCloud to be used in the future to build it out?
As we are working today, and I mean, we adapt to what our owners want. We do what they want. But our very important project now, and has been, is making data available in the shape or form that we can, and being the trusted partner where you can pick up data and do something interesting with it. And either then the open or aggregated spaces that we're working on, or cooperating with one or more of the farmers, actually going deeper into their data, like the CSA data. Why are you losing fish? Where are you losing it, and how, in what context? So then you can go in and actually change how you operate. And that's what we call digital transformation.
One of the things I remember that our colleague Krista Klavina from OVIB said is the faster they can learn from the industry side, the faster they can learn, the better.
Oh yes.
Are you experiencing that the industry members involved in AquaCloud are learning? Is this going fast enough? Do they see the advantage of sharing data?
They see the advantage, there's no discussion. I mean, I'm at every steering group meeting in AquaCloud and discuss this with fish farmers almost on a weekly basis. And they all see the common sense of it. They all agree that we are never going fast enough, but we have to learn to walk before we run. Otherwise, we're going to do what every little one do. We will fall on our faces.
So if you put your AquaCloud hat on, as you have done, and then look at iFishIENCi and iBOSS and the different demos that have been going on, and the potential there, what is your learning from the iBOSS experience?
It kind of embodies what we want to make out of AquaCloud, not as a competition to iBOSS, but being one of the inputs into it when we turn out to sea, because we're only in saltwater or sea cages at this point in time. So what AquaCloud could be is that trusted data supplier, moving data from one place to another, or gathering it, or coming in with a data set that's not accessible otherwise. So we want to have clean, good data that's accessible through easy APIs. So you just hook on, literally, you do the governance, everything is hunky-dory, and then you just turn on the lights.
Because I can imagine that 500,000 tons is a lot of data, and then you can even double that if you get all industry partners on board in Norway.
Absolutely, there's no reason to think that we won't be sometime in the future engaging Scottish and Irish fish farmers, the Faroes, Icelandic, Canadians, and even Chile, even if they're flipped up season-wise, that's sort of challenging. But that can also be repaired, because then we just map against each other.
As a scientist, it's very exciting to see, like, the more eyes we have in these different areas along the coast, and eventually perhaps even offshore. That's a Norwegian ambition for offshore aquaculture. The more we learn, not just about the fish, but also of the marine environment, you know, the effects of climate change, and then the unknown unknowns that we could perhaps uncover through more data, and data that's open and transferable and shareable.
And we see that future in our newest, or one of our newest members, called Cognizant. It's a huge company that are specialists in data analysis and all things data. They are working with a company in the Google complex, in the Alphabet complex, called Tidal X. They are sort of the skunkworks of Google. The skunkworks is where you test out all the new concepts and ideas. And then they are moving into space. Tidal X is moving into space. So we see different players actually seeing that opportunity in our industry as well. And getting more eyes on the subject is really good. Getting new sets of eyes outside of our industry is even more important, because the eye of the outsider is sometimes really keen, or you bring in values or methods from other industries that's tested and proven. So speeding up us really, really quickly.
Super cool. Great, so we want to get some of the opinions and insights from our audience, our participants here in Bergen who's with us, and also our online participants. And we have prepared some questions that I have also put into the chat. So for the audience members online, you can see these questions. The first question that we want to get to is related to the market pool. The market pool of iBOSS, for example. What would be the preferred way of having this service, this digitization of aquaculture, understanding fish behavior, controlling feeding? What's the best way for this to have this service delivered? So people online could react to that question with a comment, insight, and also a question. Frank, have you been getting input? Because we have industry members that are in our consortium, for example, Oxygard, and they have lots of clients all over Europe, all over the world. Do you have any ideas about what is the market pool, what people really want, as we're waiting for other participants to react?
Yes, maybe to introduce also what it could mean, because there is no one answer for that. Okay, when we speak about delivering service, there is both the business side, there is the technical side. So I will start with the technical part maybe first. Christian was underlying the issues of internet connectivity, which seems to be a basic stupid question, but which has been a blocking point for quite a long time in the project, because that's not so easy. First we need to agree, okay, I'm going to send you my data, but okay, I'm going to give you my data. Maybe Dorothy will listen to us, and we don't want that Dorothy listen to us. So how we do that? So historically, people were completely closing the system. If I'm disconnected from the internet, hopefully I'm safe. Not completely, maybe, but I'm safe. But okay, this cannot be done now on the long term, because we see more and more connected service. So at some point, you have to trust the system also that you can share data. So this means that we need to have these trusted partners that at least we know he will secure the firewall, he will secure the system, and if I send him some data or if I collect some data from him, then it will be trusted. So it's part of what you say as well of the trusted partner. So I need someone, a trusted partner, technical or business one, whom I could interact. And then from that point of view, it can be it can be on-premise, all managed locally, it can be delivered as a SaaS, and all business or deployment possibilities can be done. It depends also on the size of the farm. Is it only one farm? Is it several farms made by one big industrial which is able to manage its own data center? We can even have a data center in the farm If I look in HMR, so it's not yet the data center on the farm, but it's offshore. There are storms, we have internet disconnection and so on, and still the fishes need to be fed, whatever happens on the internet. So with these things also, we have to think about also on the edge. So we have distributed decoupled systems which are able to interact when there is connection, but if there is no connection, then still system is going on. So
also in developing countries where Wi-Fi internet are going to be issues from the get-go, is there a version of iBOSS that could be developed for those situations? If we know the fish behavior of this of a specific species, can we do iBOSS offline?
we can do iBOSS offline. Yes. There are several components. They can be sized. It could run on a laptop. Maybe maybe Nicola will tell us, okay, for the video analysis, I need to work still a bit, but at the end, it can run on a laptop, yes.
The worst case thing could be actually that you have a fallback option. If things massively go offline, you fall back to a program section that says, if then do so.
What we did with HMR is, okay, we are connected. If the description system is going on, and when network is back, then okay, we exchange data, we rebuild the history, and then we go on. That's.
There's a comment that says ideally this would be through the setup and having the iBOSS service delivered would be through the organizations who have the setup and configured the monitoring systems or their affiliates. Otherwise, it can get complicated where multiple providers are involved and trust security becomes even more of an issue. So this is something I think you agree with?
Yes.
Yeah.
That trusted partner, which can be an integrator, any kind of company, but that which that you have to trust, yes.
Great. Our next question, and if anybody wants to go back and comment on the previous one, that it's an open discussion, is this additional components. So we've been talking about environmental components, satiation, fish behavior, these type of things. If there's any other components that people from the industry, or even from a science perspective, would like to be developed in a product like iBOSS. Sergey, would you like, I think you just have to come here and take this, and then afterwards we can place it here. Thanks.
I think one important component is fish stress, because it affects feeding and all the results very strongly. And delousing and other manipulations like this are very stressful for fish. And it's also very important for fish to assess fish welfare and well-being. And another thing I think is important, we need to kind of shift our perspective from fish talk to me. It's a one-way flow of information from fish to the farmer, to a kind of dialogue with fish, to provide information to the fish. For example, there are very big individual differences among the fish. Fish are very diverse. It's one of my specialties. They have a kind of personality. And if you feed the fish, they don't eat all the same at once. There are some proportion of fish that don't feed. In the extreme cases, you may notice a kind of bimodal distribution of fish over the depth of the tank. Some fish don't feed. Why? We don't know. They may be stressed, they may be excluded by the social interactions by the dominant fish and so on. So we need to, one solution may be a kind of signal that food is available to the fish. That fish that are below don't feed, they may not eat. And we may schedule the feeding to include the dominant fish and subordinate fish. And for this we need signal to the fish that food is available. And it may be done in kind of several bouts. First eat the dominant fish and then subordinate fish. Signal first time, signal second time, and so on. This is just a...
Even more going in depth.
We need to dialogue with the fish.
Yeah, dialogue with the fish. Great, Sergey. And a really good point about fish stress. Nikos has a question or comment.
Yeah, actually, I will take advantage of the comment of Sergey and say that the system that we have developed, we have shown some results today concentrating around feeding. But actually, it is an online system that detects the motion and the activity of the fish. And now we are involved in another European project, the Cure for Aqua project, that we are actually focusing on the welfare of the fish. That means we try to see, based on the behavior as one parameter, whether the fish are stressed or not. And also, with another system that we have developed in the lab, we are able to detect and identify markers on the body of the fish, on the skin of the fish. The integrity of fins, for example, the integrity of the tail, marks showing injuries on the fish. That all these are marks that can accumulate and give you a final score on the welfare. And these are important, and it's really a critical issue because we have to expand the monitoring not only around feeding. We started like this in the iFishIENCi, but obviously we have to expand it further. And the final comment to the previous discussion that you have, obviously iBOSS can be a standalone application because you can have a computer in the farm. You need a computer, however, and then you can run the system there. You don't need to have necessarily internet connection. But obviously, if you have all this facility, makes your life easier.
Great, thanks for those comments. We don't need the internet to run iBOSS, but when we first have the cameras, we can look at these parameters of fish welfare, parasites, all these other. It opens up a whole treasure trove, I would think, even beyond stress and welfare, but perhaps even other things that more eyes on the fish give perhaps more ideas to the farmer.
And I even have an addition to that. When we are there, that we understand the feeding behavior properly and some of the factors affecting feeding, like stress or population dynamics within or the dominance dynamics, we need to move into operations, because feeding is just one of the aspects we need to be looking at and running. We also need to understand how the fish is doing, coping in different situations. We need to, for example, when we gather the fish, crowd the fish in prior to delicing typically, we need to understand where is the limit where the fish actually goes through fight or flight and breaks down into sort of passivity. That means they are on the verge of collapsing. And we see a lot of issues and situations in crowding where the fish is obviously being pushed to the absolute limit because a couple of weeks or a couple of days after crowding they will fall ill.
Yeah.
And even we humans, after a long period of extreme stress, exams, we actually catch a nasty cold or influenza just a week later. And that's just our immune system reacting to that cascade of hormones, just as a salmon does. There's not that big of a difference. So we can avoid pushing the fish into that corner. We are removing a lot of the secondary issues with both skin, gills and health in general. And I think that goes for a lot of species.
Any other comments on this topic? Because we have one more topic, and that is on regulations and what we are missing is from a governance perspective. Another way to put it could be what regulations, laws, incentives are missing to promote aquaculture 4.0 and digitization of aquaculture. Frank, please.
Maybe, yes, just to add, it's somewhere between that question and the previous one, because, okay, from what in the project we've been focusing on the farm, on the smart feeding itself. But now we have some, let's say, low-hanging fruits. At some point we are facing difficulties, okay, what is the feed being distributed, what is the brand, what is the type, what do we know about that feed, so we're, okay, entering some data manually. So now, probably the feed provider can send these as also JSON records somewhere that can be automatically recorded as part of the logistic chain in the system. So this will ease the thing, and I think this is not that complicated because models exist for that. And then with the fish simulators, digital twin, we start being able to predict based on the feeding what is going to be the mass, the growth of the fishes. Now, just think that we implement is we use this digital twin as kind of what if model and which can adjust. And now to the last question, okay, I know the market price are going to be here in 2 weeks, so maybe I have to target that. So target my feeding to reach that point, or I know I will have 3 different cages that will be mature at the same time. So maybe I have to regulate also internally.
So what you're saying is that the farmer could have elucidated some goals, some targets to go for, and start tweaking the system a bit and testing, getting closer and closer to those goals.
Okay, I want on this cage, on this system, okay, to go to the market on this date. So and reach that point. So, and this means that we have the farm system, and that's when we come to governance, which has to be linked to the whole chain, also from the supplier to the market at some point.
Do you even think of a situation, because we were talking about trust along the whole value chain, and from our preliminary surveys of 200 people in Hungary, 200 in Germany, and 300 in Norway, trust dissipates the closer we get to the consumer. One big thing in labeling, QR codes, could you potentially use a QR code on your fish fillet to understand the travel or the whole process of how that fish has been reared and raised, and give that kind of technological insight? Boogie.
There are systems in place with more than one fish farmer who actually do a lot of this. And it seems at this point, and as far as I know, people are not all that interested. But those who are interested are actually the retailers, because they want to say, I need to trust my supplier. So they become the sort of extended conscience on behalf of the customer. So the customer comes to the shop trusting that you have done your homework. So I don't have to make all these really, really difficult choices every time I want to go to the shop. We have prejudice as a model to avoid 100 decisions per minute. So some of them are good, some of them are really lousy. Yeah. But we use prejudice because we have made a judgment before we have to do it. So I know I love salmon. I don't have to wonder every day whether I love salmon or sea bream or mussel.
But do you love salmon because you know so much about how it's produced, do you think? Or is it just because it tastes good?
I didn't be when I was yay high. I've always loved salmon. I think it's and seafood. But it's important for me when I go to my shop, I trust the shop to have made a good choice for me. I'm also a little bit more knowledgeable about salmon than most people I meet. So I can enforce that trust somewhat by testing who is the supplier here. But I know when I go to the shop that most of that food is something I can trust. I don't go to the retailers where I don't survive that trust. But again, I have that choice in the power of my well-filled wallet. Not all people have that choice. They have to go downstairs into less reputable retailers.
Was there a comment? Yeah, sorry.
Sergey?
Just while it's coming, interesting because what you say, okay, I trust my supplier. And that's the same as what we are developing in the standard is, okay, one data supplier is being trusted by the next one and so on and so on. So we are developing the mechanism to propagate trust, but then you don't need to worry about the first one. That's
And when I trust my telephone, I don't have to think about the chipset. I trust that they have done that and validated for me. Sorry, Sergey.
A small note. The problem of trust has many different dimensions. It has a sociological dimension and also technological dimension. I think one solution from the technological part may be to use the blockchain technology. A kind of system can be done based on QR code that can be found on the packaging material of the fish, and then the end user, the consumer, can scan the code and trace the source of the fish, the welfare status of the farm, other important indices, and so on. So they can use to build more trust, because the consumers can check that fish are happy in the farm, for example. They are not dying in 70% like this. They can check the green status of the farm and so on, and can link the end consumer to the farmer, this technology. It's not like something anonymous fish coming from somewhere we don't know and found just in the store in the ready fillet form. we can try. The user can find the whole way to the fish individual in this case.
And in some cases, you can actually lean on the ASC or other systems that verify the
Aquaculture Council. Third-party labeling.
There are companies who do that with whitefish. You can screen the QR code on the fish when you buy your consumable fish. And you can then go into a web page where you backtrack to the lorry company who brought the fish from the airport to your shop, and then to the airport, the plane that brought it, in this case from Iceland, but it would be equally easy, to the actual vessel who actually caught the fish in this area, because that's important for the marine stewardship, that the fish was caught within an area that's acceptable. So they backtrack that way. To us, it would be more to handling cage, feed, whatever.
So in the iFishIENCi project, we've worked more or less bottom up, working with farmers, listening to what are the needs, looking at different species, working with the scientists, and building up this infrastructure. But if we think top down, what do we need from our politicians and our regulators to kind of meet us in the middle to propel a progression towards more digitization in the European seafood market, seafood industry?
Stable legal framework.
What does that look like?
I don't know, we haven't got it. We have something in Norway, we have probably something in the EU, and it's probably a little bit different from France to Belgium to Italy to Spain. So we need something that is at least the common denominator, where you have that red thread, so you can actually harvest fish in Norway or France or Belgium or wherever, have it produced anywhere within the EU, and you still know the source and where it's been. And it's, you know, it's been produced by within certain framework. So we don't get horse in our minced meat.
It's all about interoperability at the end, because you know there's that chain of technical interoperability, syntactical, semantical interoperability. That's what we achieve technically in efficiency. But then you can add the layer on legal interoperability and then political interoperability that you have to go up if you really want to have the business working one with each other.
Another analysis we did was to look at the 169 targets of the Sustainable Development Goals of the UN, to click out which one of these are related to aquaculture, for example, environmental parameters, water quality parameters, circular parameters, and we found dozens of those. And the idea that that's the language of the UN and of the EU, and Norway is a big proponent of the UN Sustainable Goals. So kind of we were also thinking about how to use that language to say, with this technology, we are delivering quantification of these targets that you up there in Brussels say is important, and kind of using that. You were talking about a common nomenclature, a common language. When we talk about sustainability, it's a lot of different things, but connecting the technology to these targets could help with this the political side, and understanding what we can measure and how that relates to sustainability, so we can keep progress. Are we getting better? Are we getting closer to our targets? Or are we lagging behind because we don't have data, we're not sharing data? These type of things, I think, could be a way to get closer to those more incentives and policy regulations that help sustainable aquaculture.
Yeah, I mostly agree with you. I don't disagree in any major part, but there is always an issue when, in terms of communication, where you design, you have one language to governance and another to the market. It's like the two halves of the time glass. The information dribbles between them. So the closer to the shorter distance between the governance aspect and the public aspect, the quicker information flow we have. And I don't want that time glass. I just want one chubby tube where things can flow freely and people can actually understand the information in the same context. And in terms of the FN sustainability goals, I don't think they are very implemented into public mind. They are a language that I'm familiar with because of my work and up in the system towards governance, but it's not integrated into the public mind.
I think a lot of aquaculture companies, they use SDG 2, no hunger, and promote that a lot. But there are many of the other SDGs that are perhaps even more relevant as far as jobs, sustainable jobs, especially if you go into multi-trophic. It's maybe less fish produced, but you have more jobs produced. There's social sustainability involved in that. So I think that there's a lot of work to do to get that kind of common language about how our technologies are actually helping us on a variety of goals, not just SDG 2, no hunger.
Yeah, absolutely. But I don't know how much more time we have on this, but I have sort of a pet peeve. I have a lot of pet peeves though. What we really need in terms of governance is not more governance, it's more simple governance and more similar governance between and within EU and between EU and the EEA. Because, and that is with everything, when politicians make new laws, they don't remove anything. They just build a sort of mosaic of interactive laws, and it's for a fish farmer who wants to apply for a license in Norway, or I guess in Spain or France or wherever. It's a jungle. It's a desperate jungle of laws and decisions. So you are building up a sort of a in-between layer of consultancies and workers who actually have to translate between industry and governance, and that's totally the wrong way to go. I don't mean that we should loosen up the laws, just make them simpler, reduce them, and make the processes clear. Otherwise we are in for a lot of work.
So we have a comment here, but before we want to wrap up in about 5 or 6 minutes. So if there's any other comments from the participants, either online or in the room, that's our timeline. We have Dominic Durand from Covartech. What's your insight, Dominic?
One thing we didn't talk about is the competitiveness. And I think for me it is one of the things missing in terms of the governance and the political incentive. There is a very lot of words. You have been also mentioning all this aspect of traceability, about environmental sustainability and so on. It has a cost also in the production. And if Europe wants to achieve their goals and keeping the competitiveness, there is something missing between the saying and the goal. I think this should be taken seriously, and we discussed with some colleagues what is happening in Hungary around the African catfish, for example, which is produced half price somewhere else in the world. So and then imported, and people are just looking at the price to buy at the end. The aspect of there is traceability, and I know where it comes from, and I have a better knowledge about the quality. Matters somehow, but sometimes not compete with the price. So we have to look at that, and I think in terms of the governance in Europe, this and political incentive, this has to be looked at and addressed.
Were you also referring to competitiveness between businesses, Dominic? Were you also kind of talking about that businesses don't want to share data because they're competing and they don't want to, if Frank and I are business competitors, I don't want to share my data with him, because were you also referring a little bit to that?
So I think in Norway this has been addressed, and you talked about that through the aquaculture and the standardization and so on. So at least I feel that possibly it is still there, and some data will not be shared because it will be too sensitive. So the thing is about what data and to do what. But possibly it is not the highest threshold to pass right now, or not at least in Norway. Possibly the things is somewhere else.
We're both behind the aquaculture, and the cluster as we work with is a common pain. Something is so big that we have to handle it together, because we will not be handling it individually, or the cost will be way too high, and the time frame is unacceptable. So that is always a good way when you have that burning platform.
I remember having this conversation with one of Krista's colleagues at Ovum. I asked, okay, is data sharing a problem? And this was also in the context of One Ocean Week in Bergen, where we were talking about this issue of sharing in making digital twins. And Ovum said, no, sharing is good. We do better business when we're learning. There's no competitors in data. Data should be shared. And that was a very cool angle. It shows, some businesses have got over that that old idea of my data is mine and that's my competitive advantage. No, actually, we're seeing very strong reasons why data sharing gives you that competitive advantage. So I think that's one of the major learning from the iFishIENCi and iBOSS process that is also corroborated with AquaCloud. Yeah.
Data is like love, it grows when it's shared.
Oh, Boogie. We all love data. There's a question from the audience that I got, and this is on water quality. So I'm wondering if it's Christian or Gianmarco or Nikos who can answer this. Did the automated feeding result in better water quality due to less feed wasted? I see Gianmarco making his way towards the microphone.
You're describing it like a sports event.
Live sports.
Yeah.
So, as I said before, the experiment was performed in the same system at the same time. So we usually don't take single parameter from each tank unless it's specifically required, and as a system there is a full reutilization of the water. So it's difficult to understand at this stage if there was also let's say better water quality in the automatic feeder based on the scoring system compared to the normal one. We might repeat a trial or perform a trial let's say further to address just one of the two type of system to see if this one reflects also in the water quality. What we know in the tank that was fed by the scoring system, the amount of feed that was provided was less. So we know and tomorrow we're going to talk about the sludge collection and the waste to value. Of course, the main amount of nutrients are coming from the digestion, the product of the digestion and absorption of the fish, so coming by the feed that is provided to the fish and the uneaten feed that is provided to the fish. So theoretically yes, but we cannot still answer to the question.
But summarized, we have the data, but we haven't correlated that to exactly better water quality.
Yeah.
Yet.
We can say that we are at the preliminary stage at the moment.
And then there was a previous question asking about the water quality parameters, if they were used in the feeding. And what I understand is we're collecting that data, but we haven't then correlated that into the algorithm. Is that correct, Frank? Also,
yes. For the timing, yes, both have not been used jointly.
Yeah. Great. So I'd like to round up, and I'm wondering if Tomasz, if you could maybe come up and help me say a few last words, kind of wrapping up the iFishIENCi and iBOSS experience. Also a preview tomorrow, same time, same place, here on the waste to value workshop, where we're going to go into the circularity aspects of iFishIENCi. Tomasz, are you happy with iFishIENCi as a project as a whole? It was very ambitious, hitting lots of different aspects of feed and genetics and data sharing and data interoperability and iBOSS and algorithms, and also working across these many disciplines of biology and AI, applied mathematics. What is your take, and what is the future of these type of collaborations?
Of course, I'm very happy with the project, and it was especially very good to see today and previous events of the project that we decided to go in the right direction. The industry is hungry for data. We need data, and sometimes we have this data already, but we did not use this data. And iFishIENCi provided a good structure, framework, or platform for that to collect and organize this data and provide it for the industry in many ways. I think not just the iBOSS, but also in our work on the genetic field, we used the knowledge which was not exactly new for the industry, but we tested it and improved it. And I think the way ahead can be seen very, very, very well after this meeting as well, that we have to go in that direction to support the industry to fulfill the requirements of the competitiveness, to fulfill the requirements of the new legislations, new EU regulations. And I want to mention here that we are always talking about the EU regulations, and we consider this regulation, this is coming from the European Commission or from the politics. But it's not coming from the politics. It comes from our consumers. It comes from our future consumers. If we ask our kids how they think about the industries, not just aquaculture, but in general the industries, they would ask us, how is it possible that you are still supporting investments which are not sustainable? So it's not something from the political environment. It's from our future, this message that we have to go in this direction.
Or we are the political environment,
Yeah,
so as
yeah,
consumers and the broader consumers.
Yeah.
So great. I want to thank Frank and Boogie and Tomas and everyone who participated today, all of our guests here in Bergen and online. Tomorrow we have the Waste to Value workshop that starts at 10, from 10 to 12 tomorrow. And thank you for all tuning in, and we will see you tomorrow morning.
Thank you, Dorothy, for a nice
Yes.
moderation.
Thank you.